The last problem we're going to look at involving these accelerations caused by forces at funny angles is a really important one because it stands in for a lot of other problems that you solve in physics, which is what happens when you have an object which is sitting on a slope like this. What's going to happen to this object? Now, we all have a pretty good intuition that the object's going to fall down that hill, and we want to look at how does that come about from the forces that are involved here. So if we have a quick think about what forces are involved, it becomes pretty clear pretty quick that one of them is going to have to be gravity. So there's gravity. Gravity always points down, and gravity has a strength of m, the mass of the object, times g, the strength of the Earth's gravitational field. In this case, let's say this car weighs 500 kilograms. Right? Pretty small car. And if g is 9.8, as it is near the Earth's surface, then that means the force of gravity in this case 4,900 newtons. Okay, now if we think hard enough about this, we're going to see that there's another force involved here, which is, well, the car's not just falling downwards, so we know gravity can't be the only force. It's touching the road. And if two things are in contact, you're going to have a force pointing perpendicular to that contact. So we have a contact which is acting in this direction, which means we're going to have a force acting on the car in this direction. At right angle, pointing away from that slope. We call that force the normal force, or sometimes called the contact force. Same thing, different name. Now, something weird should strike you at this point, which is that we have one force going this way, downwards, and another force going up and to the right, and yet somehow these two forces combine to give us an acceleration in a third completely different direction. Okay? So we need to analyze this, and our go-to trick for analyzing a force problem involving multiple forces should be that free body diagram. The free body diagram, remember, where we take the object and we just turn it into a single dot, and then we arrange our vectors head to tail. So let's start with gravity because that's the one we know the strength of. So that's 4,900 newtons downwards. And then now we're going to put the normal force in, and I'm going to put that pointing upwards like this. There's a couple of things we do and don't know about that normal force. We know what angle it's going to point at. Well, because if the angle of the slope here is 25 degrees, then it turns out if you do a bit of rearranging in your head, you'll soon see that that means that angle there is also going to be 25 degrees. So if the angle between the ground and the slope is 25, then the angle between gravity and the normal is also 25. And that works for whatever angle you happen to put the slope at. So this normal force, what we don't know though, is how strong is this normal force? Is it this strong? Is it this strong? We don't know. But of course we can work it out. And what we do is, once again, we take off our mathematics hat and we put on our common sense hat, and we realize that the car is going to go down the slope. So any net force we get has to point down the slope. So what we can do is we can take a sort of a parallel line, we can take this slope here, we can put it on here, and we can say, once we add up all these forces, I don't know what they were, how strong they all are, I don't know exactly what they are, but I know that I better end up somewhere on this line. Because if I don't, well, let's think about what would happen if I don't. Suppose I have a normal force which takes me past that line. Well, that would mean that the car would be accelerating in a direction not down the slope, but away from the slope. If the car's accelerating away from the slope, it's starting to fly. We don't see that happen. On the other hand, If the normal force were too weak, if it were down here, well then we wouldn't have a car which is accelerating down the slope. We'd have a car which is accelerating into the slope. We'd have a car which is burrowing into the hill. Once again, cars don't tend to do that. So we're pretty sure we have a normal force here which ends at such an angle that the total acceleration of the car points in this direction down the slope. So what we've got here is a gravitational force. We have our normal force, unknown strength, and then, as with all of these free body diagrams, from where we start to where we end up, that's our net force. And I always draw my net force in some other style to the way I've drawn my regular forces, because the net force isn't really a force, it's just what you get when you add up the others. So that's the net force there. But what have we got? We've got a right angle triangle again. So, once again, we can use our good old friend, trigonometry. Now you might wonder, why is that a right angle? Well, if we define the normal force as being at right angles to the slope, and we're saying the net force must be down the slope, then by definition, those two things have to be at right angles. And that's exactly what that angle there is. Okay? We've got our trigonometry here, so we can say, okay, we know the length of this long side, the hypotenuse. We know the angle here, and we're looking for the net force because that's what tells us about accelerations. So, F net is going to be equal to 4,900 newtons times sine of 25 degrees. Now, you can work through this problem using any angle you like and any mass you like here, and what you're going to find more generally is that F net equals mg, that's the length of our hypotenuse, the size of that gravitational force, multiplied by sine theta, where theta is the angle between the ground and the slope. So this one here, that's our general formula for the net force of an object which is sitting on a slope, just being acted on by gravity and a normal force. Alright, but lastly we wanted to find the acceleration, not the net force. How do we go from a net force to an acceleration? We divide by the mass. So, in this particular case, the acceleration is going to be 4,900 newtons times sine 25 degrees divided by 500 kilograms, which I for one can't do in my head, so I'll get out my calculator. We get 4.14 meters per second squared. Now, that kind of makes sense. If gravity is acting alone, no slope, nothing, we have 9.8. If an object is just sitting flat on a slope and is being perfectly balanced, the normal force with gravity, then it doesn't accelerate at all. 4.14, it's about halfway in between 0 and 9.8. Alright, what about more generally? What if we just have a mass of m? Then what's the acceleration going to be with an angle of theta? Well, we're going to just take this, we're going to divide through by m, but that means we're just going to divide that m off, so we're going to end up with g sine theta. And that's our general acceleration for an object which is sitting on a slope, being accelerated downwards by gravity, but upwards by that normal force, and we get something which depends on the strength of g, but also depends on that angle there.